Welcome. So today I'm going to speak about the anatomy of a large-scale real-time spam classification system. I have a bit too many slides, so I'm going to have to rush a little bit. I'm sorry about that, but hopefully it will be understandable. So this was a project between Futurice and Supercell. Involved several people at different times. From Futurice, it was Tero Nurmiluoto, who's actually over there, Teemu Kinnunen, a data scientist from Futurice, and myself. And from Supercell, this was led by Jessica Holmeyer, the anti-fraud lead. And we also involved some Supercell developers in building this. So what's the problem? What are we trying to solve? So this is how spam looks like. So the games have chats inside, and you can join channels and talk to other players. And these are free-to-play games. So spammers create accounts and with bots start sending messages, all kinds of different types of advertisement. And this obviously creates a bad experience for the users, and it's not what it was intended for. When we started this project, Supercell already had an existing classifier running in their chat servers. And this spam filter had very high accuracy in the training data and in validation. The problem was that in practice, it was very easily circumvented by the spammers. The setup they had, the architecture they had, is they had training with EMR, starting the model in S3, and then the classifier that was running on the chat servers would load the model parameters and classify the messages in real time. These posed some drawbacks. Mainly, adding features was slow and risky because every time you added something, you were touching the actual chat server, so you could bring the chat down. Game developers had to be brought in to actually put things in place. The new changes needed to follow the game server deployment schedules, and we were tied to Java because that was the language the game servers were written in. So our approach from the start was make large-scale spamming too difficult and costly to be profitable. This means that we were not intending to get rid of all the spam. We were intending to reduce the problem to the point where it wouldn't be such an issue. It is very, very difficult and challenging to totally, completely eradicate spam. Our approach had 3 main steps. So first, we would create a process for generating labeled data. So that is messages that are labeled as spam and messages that are labeled as ham. We would measure the quantity of spam and the classifier accuracy that is live in production, and we would iteratively improve the classifier and check how it's performing. We would decouple the spam classifier from the game servers, so we would like to not have to involve the game development teams when they're developing, and also be able to apply the classifier to many different games, regardless of their infrastructure and architecture. So we plan to build a REST service that can be used to classify messages. And then we would improve the spam classifier by improving the way it detects spam based on the text itself, and also taking into account contextual behavioral features, so how the accounts are behaving, because bots have specific traces that humans don't. So this is the architecture. There we go, typical. We've got the cloud, spam coming in, and magic happens. Okay, so this is how it looks like, actually. We leveraged AWS extensively, and we were a pretty small team, and actually not that experienced in the start with AWS, so the AWS truly delivered as we built it. But there's main component of real-time classification and one big area for model training. And I'm going to go step by step on what this is. I'm not going to describe here. So from a high level, this is basically what we have. So we have event data in S3. That means everything that happens in the game, well, not everything, but most of what happens in the game, what the accounts do, what channels do they visit, what messages do they send, what battles do they do, that gets tracked by Supercell and stored as events in S3. And we built our system connecting to the event streams, both what they had in S3 stored, as well as the live event stream from Kinesis. And in that sense, our system is completely decoupled from Supercell's existing game servers. Like we don't access any database. And for training, we start from event data. We send it to an annotation tool we built, where annotators label messages as spam or ham. And then we store the annotations in S3. And then we have a process of training the models based on the label data. And we store the models in S3, the trained models. And the chat servers in real time send messages to our classifier service, which has the models in it and classifies the messages. And in order to classify, it needs context, so behavioral context of what the accounts were doing. And we store that behavioral context in Redis. And you have Kinesis client library. Basically, we were tracking the events coming from Kinesis in real time. So the battles, the chat messages, everything that's happening in real time, keeping track of that and storing in Redis to be used by the classifier. Why do we need this label data? So why do we need these annotations? The problem with spam is that it's non-stationary. So past data does not predict future performance. And that was already clear from the start based on the existing classifier. In particular, spammers don't change their behavior unless it's necessary. So we can see the same exact type of messages for a year. And only once we start blocking them will they actually change it. It's highly, and once they change it completely. You never see that message anymore again. So the fact that you learn a classifier that does really well in the past means very little from what you do in the future. So we needed to be able to track these changes and understand how we were doing. We also had an existing label data set that was limited in size and scope, and we examined Crowdflower, Amazon Mechanical Turk, and these other solutions where you can basically get annotators to label data, but they were a bit too costly. So we decided to build our own. So a bit more explanation, why did we need this feedback loop? So if you look at the graph in production, it looks like this, and you have green there as ham and red there as spam. How do you know this is working? So do you deploy something new? How do you know that the thing that you just deployed still works? You can't really know because you don't know if that spam is truly spam or is it ham being labeled as spam. You don't know if what you're labeling as ham is actually spam. There is no way to know this just based on the data. There's no clear feedback loop without us creating one. So this was our approach. We sample data from S3, these events, these messages, sorry, and we store these unlabeled messages in an annotation tool that is backed by a Postgres database. This annotation tool is basically a browser application where annotators go regularly, check some messages, and just press is it spam or ham and give some details. And on a regular basis, then, with another cron, we end up storing this newly labeled data in S3. After that, we do context augmentation. So we have the messages labeled spam or ham, but we also want to know what the accounts were doing at the time they sent the messages. So why? So spammers have very specific behavioral patterns. I'm not going to go into too much detail about what they actually do because for obvious reasons, they can be watching this. But essentially, if you think about it, a bot will do things much faster than a human. It will send messages with certain characteristics over and over again. So there are specific things we can track. This kind of behavior is also harder to hide. Spam messages, text itself, there's many ways you can vary text, make variations of text and still deliver your message. However, the behavior itself is somewhat harder to change because you still need to, the spammers still need to visit many channels, they still need to send many messages in order to actually get the spam across. But how do we get this context? So how do we figure this out? There would be two options for this that we considered. One would be we implement some tracking. So let's track what channels an account has visited. We would implement it. Okay, so I have to explain a bit about this. But so the chat server, so we have here in Elastic Beanstalk, which is an AWS service, we have our classifiers running. And we get the messages coming in. We could be tracking other things here, like other events here of what the accounts are doing. And also from the event stream in Kinesis, we track it and store it in Redis, and we have access to all these things that the accounts are doing, what they're visiting, whatnot. We could basically take a snapshot of that and store for training later, right? What would be the problem? So if we do this, we have this issue that, okay, we've labeled many thousands of messages from the past. We add a new feature. This new feature is only available for future data. All the past data we spent money on labeling becomes kind of useless, or we have to make up some values to fill in where the feature is missing. So this is pretty annoying. So we consider the second option, which is we have all the events already in S3 stored for history, so like what the accounts were doing 3 months ago, 6 months ago. Why not replay history? So pretend we were 6 months ago, replay history, and figure out what each account was doing at that specific point in time, and use that as a feature. So okay, this account had visited 10 channels before it sent this message. I'll use that as input for the classifier. One good thing about this as well is that we can update the training set without touching the real-time production system. So we can just touch the batch system and change these things. The disadvantage is now that we have 2 points, 2 different places where we have to generate features. We have one where we do from history, we replay history and generate features from it. But we also have the real-time part where we're generating features in real time from what the accounts are doing, like with seconds of latency. And this is added complexity and cost. Just a bit of primer. So we used, for this batch replaying of events, we used AWS Batch. And AWS Batch is a fully managed service from AWS, where you can define some task, some job as a Docker image. And this image has the application you want to run, and it is defined by a reference and arguments. So typically what you end up doing is you define some sort of task that loads data from, for example, S3 or a database, does some sort of processing, and then stores it back in S3. And the actual processing is all managed by AWS. So AWS will spawn the instances, run your image, and then kill the instances after that. It's a very nice way to basically do parallel processing. Okay, so after the primer, back to how do we actually gather this past context. So let's say we have an account, X, and this is kind of what we see in the data. So the account was created, it sent a message, sent another message, maybe it joined the clan, it sent some messages, it had a battle, and whatever. And we have all these streams for all accounts of what they were doing, sorry. We have this challenge here is that when a message comes, this is real time, we need to determine immediately whether it's spam or ham. We cannot wait one day and then run some batch process and figure out then whether it was spam or ham. And we can only use information that was available at that point in time. Like I cannot use the information that account X at the time that it sent the first message, I cannot use the information that it had sent 10 messages because at that point in time I didn't have access to that. It seems weird that I'm talking about this, but remember that we have all the data in S3, so we could have access to this. But training a model with that data would be useless in practice, or almost useless in practice, because in practice, we have to react immediately when we have very little data available about each account, potentially very little data about each account. So the solution was to replay these events. That's what we decided to do. And with AWS, what did we do? We implemented a Java application that loads events for a date range. So all the events for all accounts for, say, 2 days. It replays all the events in order, what each account was doing, joining a clan, sending message, sending message, having a battle, doing other things, all kinds of events we track. And we keep this current state of what each account is doing in memory while we do this processing. And we store snapshots. So every time a message is sent, we store a snapshot of how it looked like at the moment in time. So how many channels a certain account had visited at that specific moment in time, and other features like that. So we have a good representation of what we will get in production when we are doing this in real time, not when we are replaying. It has to be exactly the same. And this actually we kind of package this in a Python script. So in order to run this in parallel for example, a month, we can just run a Python script that will spawn jobs for different data ranges and basically process many, many terabytes of data in a few hours. So all managed by AWS. Okay, so this was the stream replaying. Now we have to do the same thing in real time. And in real time, we're not getting events from S3, we're getting events from Kinesis. Kinesis is where the events end up. Yeah, so we use the KCL library, which is provided by AWS, which is a library that can read events from Kinesis. Many game events these are technical details, but many game events are batched into the same record. So this ends up being very efficient. We can actually track millions of users, multiple thousands of events per second, with basically 2 very modest instances. We implemented event processing so that it's idempotent. So what does that mean? Is that if we process the same events over and over again, we get the same result. And that's something that is important when you do stream processing, because sometimes there are errors and events are replayed, and you definitely don't want to replay some messages over and over again that make players look like they're spammers. We relied on Redis to store the context, so we store the behavior in Redis. Why Redis? Redis is very fast. We don't need persistence in this system, so we don't need to store the behavior of the players from last 10 years or last 5 months or anything like that. For this part of the system, we only need the behavior right now. So Redis is good for that. It also has some really good data structures, sorted sets, and TTL that really make it efficient and somewhat easy to implement the kind of features we want. Almost all features we have relate to, or a good amount of them relate to basically tracking what the account was doing in a short time period. Because where accounts can be created and start spamming immediately, it's rare that we can rely on long-term behavior. We need to be able to determine whether it's spam or ham based on behavior from very short time periods. Yeah. Okay, so with the batch processing, we got the training data. So with the stream replaying, with the Kinesis processing, we get the data in real time. So we have the data available. So let's train a model that could make use of this data and actually classify messages. So we have our data in S3, and this is the message plus context. So we have features related to the message, related to the actual text in the message, and we also have features related to what the account was doing and other related contextual features. And this is just basic supervised learning. So we have this input, and output is the labeled, annotated label, either spam or ham. And we have data set with more like millions of samples, and we add them on an almost daily basis, new samples to it. We trained some models in EMR and some in EC2. Pretty much, the data set fits in memory, so we don't really need any. For training, we don't need any big data tools. We check the accuracy of so when we train these models, and because the data is changing all the time, this is all automated, we check metrics. So we check, is our model after being trained having many false positives? It doesn't get deployed if it has many false positives, for example. That's something we care a lot about, so we don't want the classifier to label normal ham messages as spam. So some challenges with adversaries. Accuracy in past data, like I mentioned, is not representative of future accuracy. We've seen that adding new features can sometimes make it more brittle. So we want to track some new thing. We add it to the data set, and what happens is that the models can quickly see that that feature is really good and learn that they can trust it. But the spammers can, if we track certain behavioral features, for example, it might be a behavioral feature that the spammer can change. So it didn't have any reason to change that before, but from the moment we start blocking it based on that, they will change it, and then suddenly we went from a classifier that worked to a classifier that completely fails, because the classifier overfitted to that specific feature that worked really well, but it only worked really well for past data, and they could change it. Also, classifier chaining, so when you met a classifier and another classifier that takes input, the output of the previous classifier, a similar problem. So basically, we start having dependencies where you can make the system brittle as soon as you can make one of the classifiers brittle. To try to tackle this, the goal is to try to find decision spaces that are hard to manipulate. So that's why we end with, for example, adding contextual features, behavioral features. So the text itself, the actual messages, you can easily change the text to try to get around. It's also important to try to foresee problems with the classifier, and, for example, generating synthetic data to cover certain problems that you might already foresee will happen. Hi, Temu. You actually worked on this project. You just joined. Yeah, so more challenges with this. So if you think about it, the decision space for arbitrary strings in 20+ languages is enormous. So the amount of possible ways you can write messages, that you can obfuscate messages, add random characters in between the messages, space them out differently, use different characters to make shapes. There is many ways you can transmit your message using completely different text. And classifiers overfit too easily in this setup. And the typical approaches you've seen in the literature for text classification fail horribly in this kind of setting as well, if they are applied directly. So I cannot go too much into details, but the main idea is to try to convert the original text into lower dimensional spaces. Such, for example, similar to our convolution creates translation invariance, where it doesn't matter where in the picture you see a certain shape. We try to apply transformations that create obfuscation invariance, so that a message that is obfuscated gets transformed into a message that is not obfuscated, and it's in a kind of like reliable way. And as I cannot give many examples, but here is an example. For example, if someone would write QQ2 space 3 space 4 space 5 underscore whatever, and wait, this line here, I don't know the name, you would convert these to something like this before you apply a classifier. So this is actually quite tricky to do in general, because there are many ways, again, to obfuscate, but it's very important that we do this kind of de-obfuscation before feeding the data to a classifier. We also try to process more than a single message to detect obvious repeating patterns. Now, the classifier nodes, so this is more about the service, not the actual models. We run it on Elastic Beanstalk, and I'm going to talk a bit about what Elastic Beanstalk is. So this was actually a really useful tool from AWS. It's an easy way to basically have an auto-scaling group, a load balancer, and some nice deployment tools. This allowed us to scale to many thousands of requests per second without almost any operations burden. So we don't have. It's rare that the system has problems. It's extremely rare that we've had issues with the actual production system. And we don't even have a staging environment, actually. So we managed to, with unit tests and with A/B testing, we actually managed to mostly rely on the production service. This AWS Beanstalk, among other things, provides us with rolling deploys. So we can, when you deploy a new version, it creates a new environment that's the same as the existing one, puts the new code in, starts feeding a little bit of traffic, sees if the health is okay, and when everything is okay, it swaps to the new one and drops the old one. So all of that is managed by Beanstalk, and if there's a problem, it will revert to the old one. We don't have to take care of any of that. Also, with this, we also have these immutable instances. That means that we don't have to care that maybe the state of the EC2 instances goes bad. That is a problem if you use some traditional methods of deployment. And we got monitoring and logs from CloudWatch. And it was really easy to use. We didn't have much experience with AWS prior to this project, and it wasn't that difficult to get started with this. The actual classification system is a web server with a REST API and basically one endpoint, classify, send this, classify this. It polls S3 for new models, and polling is fine here because we don't really need to adapt. We don't need to bring a new model every second. We can check every few minutes and just see is there a new model there and load it if there is a new model. We have a filter that's composed of multiple distinct classifiers. And we are deployed in the same regions as the game servers. So both the classification system and the Redis servers are in the same region, AWS region, as the chat servers, so that they are very close by, and there's very little latency, millisecond latency between the chat servers and our actual classification system. Even though we're actually in a completely different, separate account and like completely isolated. We do A/B testing. So our main production environment, we have basically two. We always deploy to the site B first, and we put very small amount of traffic through it, and we check that everything's okay. And when we are confident that the statistics look okay, we deploy to the main one and swap the traffic back to the main one. We designed the system to fail gracefully, so if for some reason something went wrong and we are not tracking certain features, we want it to let messages go through, not to block. We don't want it, this actually requires careful thinking, that we don't want it so that if for some reason something starts failing and we stop tracking certain features, that those features get to values that lead to spam, to being detected as spam. And this setup is pretty much horizontally scalable as long as Redis scales. So of course it's not completely scalable in the sense that we need to shard Redis, but we haven't had any problems with this setup. Something that I didn't show in the architecture, but we also do banning based on annotations. So we not only use annotations for training, but we also use it to literally just, okay, let's ban these accounts that are basically spamming, and that we know because they have been labeled by some human. Some person went there and labeled them. We also do rate limiting and locking to avoid brute force attacks. So much like you have on your phone, you cannot introduce lots of pin codes because obviously you could just figure out the pin code by trying many. Here we also have to do something similar because an attacker can just try many different messages, and if we don't somehow limit them, they will figure out eventually how to get through. So essentially, if they start somewhere around in this space of ham and spam, they can just keep changing their messages and move around in the space until they end up in ham. They cross the decision boundary. Yeah, so this is just a high-level view. So quick retrospective for this. Things that we could have done better. We should have thought a bit better about tooling for changing labels of already labeled data. So the annotators label the data, but we don't have good tooling for investigating the already labeled data and changing after the fact, go and change, for example, the labels of data that has been labeled a long time ago. We can do that, but it's not very easy. We should have introduced this human-based annotation banning earlier because it works well, and it's an example of a hybrid approach where you use humans and an automated approach, an automated system, and it is currently one good way, one important way that the classifier is able to detect spam. We implemented this real-time stream processing in a separate repo than this replaying of events, but they actually have to do the same thing, and this was a mistake. So they are highly coupled in the logic, but it's hard to make sure they're doing the same exact calculations, and if they don't, the system fails. So that was not a very good decision. And another thing that we learned from experience is there is real cost in adding features. And any feature that you can't just generate on the fly, that you actually have to go and dig from data sources, means that you have more dependencies to other systems, and more ways you can fail. And also, you have to track more data, so the costs increase. Results, so we got highly decoupled chat servers. So we never caused problems to the production system, Supercell's production system. if we had any issues, it never impacted anything that they were doing. Our spam detection rate is multiple times better than the previous model. However, the spam problem is not solved. It's an ongoing battle. Machine learning with adversaries is really hard. We're looking for data scientists. Futurice is looking for data scientists. Supercell was looking also for data scientists, especially to fight the good fight and against fraud. So if you're interested in that, you can ping me.